Next on the menu is a minor of a matrix. For an element Aij in the matrix, its minor is Mij. This basically means deleting the row and column of the element and finding the determinant of the remaining submatrix. Let's take an example here. Find M22 in matrix A. First off, you identify the row and column of interest. Next, you delete them from your view and consider the leftover submatrix. The determinant is AD minus BC as you saw earlier. Now simply substitute the values to give you. An interesting application of minors is in determining the inverses of a matrix. The inverse of a matrix is essentially the matrix equivalent of reciprocal. So it's just as a number 5 multiplied by 1 over 5 gives you 1, a matrix multiplied by its inverse gives you the identity matrix. That's special grade with 1s on the diagonal and 0s everywhere else. To find this inverse, we need to upgrade our minors into something called cofactors. This brings us to the checkerboard of signs. Imagine overlaying a grid of plus and minus signs on your matrix, starting with a plus in the top left corner and alternating. To get a cofactor denoted as Cij, simply apply the corresponding sign to the minor you just calculated. If the sign is negative, flip the sign of the number. If it's positive, leave it alone. Once you have calculated the cofactors for every single element, you arrange them into a matrix. But we aren't done yet. We need to find the adjoint matrix. This is done by taking the transpose of your cofactor matrix. Transposing is just a fancy way of saying swap the rows and columns. The first row becomes the first column, and the second row becomes the second column, and so on and so forth. Now we bring it all together. Remember that determinant we talked about earlier? The formula for the inverse is 1 divided by the determinant multiplied by the adjoint matrix. This is why it was so important that the determinant isn't 0, because you can't divide by 0. So we take that scalar value 1 over the determinant and multiply it into every element of the adjoint matrix. The result is your final inverse matrix. Let's step back and look at the geometry. Because a matrix is much more than a spreadsheet of values, it is a machine that transforms space. Imagine standard 2D grid with vertical and horizontal lines making up the fabric of the plane. When you multiply a vector by a matrix, you're essentially warping that grid. You might stretch it, rotate it, shade it, or reflect it, but the origin always stays fixed, and the grid lines remain parallel and evenly spaced. Here's a secret code to reading a matrix geometry. The columns tell you exactly where your basis vectors land. The first column of the matrix represents the new coordinates of I hat, the unit vector that originally pointed along the x-axis. The second column represents the new home of j hat, the unit vector that originally pointed along the y-axis. Once you know where these two land, every other point in that space just follows along relative to them. This geometric view illuminates exactly what the determinant actually is. Remember that calculation AD minus BC, it isn't just random algebra. It represents the scaling factor of the area. If the determinant is 3, it means your transformation takes a specific region within an area of 1 and stretches it out to have an area of 3. If the determinant is negative, it means space has been flipped over, like turning a piece of paper upside down. And if the determinant is 0, it means the grid has been squished flat onto a single line or even a point, destroying the area entirely. This explains why a matrix with determinant of 0 has no inverse. This gives us the meaning to what we calculated as our inverse matrix. If a matrix transforms space, say by rotating it 90 degrees and doubling the size, the inverse matrix corresponds to a specific transformation that undoes that action, rotating it back and shrinking it down, perfectly restoring the original coordinate system.